This video is going to cover bending stress. Bending stress is another type of normal stress, so it does use the same exact sigma, but to make sure that we know the difference, it has a little sub b. Now, bending stress is another one of those very simple equations. It's simply m times y over I. However, these variables are kind of not clear as to what they really are. M is moment, and that's pretty simple, so it's bending moment. Y, though, is the distance to the neutral axis, and we'll talk about that in a bit. Lastly, I is moment of inertia, which we covered last time. So, very simple equation, but the big thing about this is the distance to the neutral axis. And the best way to explain this is to literally pop into an example, but first off, let's just look at a basic rectangle. The neutral axis is at the centroid of the cross section. And the neutral axis can be either x or y directions. So we have x and we have y. So the centroid of this cross section has two neutral axes, the x direction and the y direction. If we're doing bending in the x direction, then our distance to the neutral axis is in the y direction, out either direction that you want to go. So for instance, if you wanted to find bending stress up here at point 1, then you would use this y. If you wanted to find bending stress down here at point 2, you would use this y. So that's why it's y, but that is very specifically in the x direction. And if we're in the x direction, moment of inertia is also in the x direction. However, if we're in the y direction, if we're doing bending in the y, then instead of having y, maybe you want to call it x, because then to our point number 1, we're going this direction for x and this direction for x for point 2. So perhaps you want to just call it y because we're bending in the x direction, and then you maybe want to call it x when you're bending in the y. But the moment of inertia is always, of course, about the same axis as our bending stress. So what we're going to do is we're actually going to see this in an example. And why is it called the neutral axis? The neutral axis is the point where there's 0 bending stress, which should make sense, right? If you're at the point, say right here, on the end, I guess we'll call that point A. If you're at point A on the neutral axis, and we are looking at doing neutral axis bending about the x-axis, so if we're doing bending about the x, and we're on the neutral axis, then our value for y is 0. And the reason it's called the neutral axis is because there is 0 bending stress along that axis. Again, remember that that axis is at our centroid. So let's see an example. This shape is the exact same shape that we did last time when we were covering centroid and moment of inertia. So if you want to see how to calculate centroid or moment of inertia for this shape, go give that video a watch. And what we want to do is we're going to find stresses at 3 points. We'll call this point over here point A, we'll call this point down here point B, and we'll call this point over here point C. So if we draw in our neutral axes, we know technically that for y, the distance from the outside face over, this was x bar, and we knew that x bar that we calculated was 3 inches. Now I did rotate this shape 90 degrees, so that'll be ever so slightly different. Where I say x now, it was y. Where I say y now, it was x. And our centroid in our new direction here, up to our x-axis, that new one that we are going to call y bar, that value was 2.38 inches. So our centroid, as a reminder, is about right here. And we did already calculate what Ix and IY were. Again, remembering that I'm rotating these 90 degrees, so therefore they're going to be flipped from last time. So 55.1 inches to the fourth for IX, and IY is 81.3 inches to the fourth. So again, what do we want to find? That's just some givens that we had from last time. This time, we want to find the bending stress at A, B, and C. And in order to actually have bending stress, we have to have a moment. So let's have a moment, but we're going to solve this problem twice. First, we're going to put a moment about the x-axis. So I'm going to put my moment, I'm drawing it about the x-axis. Technically, it's going to act at the middle about the centroid, but I'm going to come back in and I'm going to move this one in a bit, so we'll just draw him about here. Or well, I guess we could move him. We'll put him here. So there we go. There's our moment about the x-axis. And our moment, let's say that our moment is 24 kip inches. So the first time that we're going to do this, this is bending about the x-axis, correct? So the moment is about the x-axis, so we're going to be using bending about the x, which is m times y over ix for every single one of these. And again, y is the distance to the x-axis in the vertical direction. So we'll do them each one at a time, starting with A. So we have sigma bending in the x direction about point A here. This is equal to m, and m we just said was 24 kip inches. Y for this guy, let's draw it out. I want to know how far A is down to my neutral axis x. And to do that, I could think of this in a different way. I could think of it as it's a total of 6 inches tall, and then subtract out y bar here. I think that's what I'm going to do. I think that would be a nice, really easy way to think about it. So again, I have a grand total of 6 inches of total height, and I'm going to subtract off y bar, which was 2.38 inches. And then divided by I, again, this is ix, because we're bending about the x, so 55.1 inches to the fourth. And what we're going to find is 1.58 KSI. Now the question is, positive or negative? Technically, this equation that I'm using is ever so slightly different from what the book uses. The book will throw a negative sign in here, but instead of actually trying to play with signs and directions, let's just think about it. Let's think about it. Remember that a moment, right, a moment is created by a couple of forces, correct? So those two forces are going to cause rotation, which is a moment. So if you think about it this way, you have coming out of the face. You're coming out of the face. That's going to be the tension side. And wherever your arrow is pointing into, that's of course an arrow, big arrow going down, that's going to be compression. So if you're pushing into the face, following your lovely arcing of your moment here, if you're pushing into the face, that's going to be compression. If you're pulling out of the face, that's going to be tension. So on the top here, because our arrow is pointing into the face up at the top, this is going to be compression. Which again, compression is negative, technically. We can always denote it with C and T. Next we have going on at point B. And again, so now we're looking at the bending stress in the x direction at point B. Point B is down here as a reminder. So we have m is the same m, it's still 24 kip inches, times y. What is the distance of these two? I'm going to say that that's a total distance of y bar minus the 1 inch. So how I'm looking at this is I've got this whole y bar, and then I'm going to subtract off this 1 inch, and that'll give me the remainder. So we said it's y bar minus 1 inch thickness down there. Over, again, I and the x, which is 55.1 inches to the 4th. And what we're going to get when we solve for this is 0.60 KSI. But because we're on the opposite side of the neutral axis, we're on the side with the arrow coming out of the face, we are now in tension. Right, we are now in tension. And lastly, for point C, we have the bending stress here. About the x-axis for point C is going to be equal to m, 24 kip inches, times what for C? Well, the distance that C is to the neutral axis is very simply y bar. Right, that is quite simple. So y bar here, divided by I, again, 55.1 inches to the 4th. And we're going to find that for C, it's 1.04 KSI. And again, since it's on the side where the arrow is coming out of the face, that does make it also in tension. Okay, so it's a really, really easy, simple problem here to solve for it. But now, just for the sake of being a little different here, let's go ahead and let's rotate our moment. Let's do it all over again, but this time our moment is going to be going the other direction. Let's see if I can't clean this up without removing everything. Nope. We were so good and then we weren't. Well, we might just have to leave that one there. Anyway, new moment. Let's say our new moment now is going this way. Same value for m, same 24 kip inches. But this time, we're still finding stress at A, B, and C, but this time we're bending about the y-axis. So because we're bending about the y-axis, we have a new equation, right? That was god-awful ugly. So this time we're bending in the y-axis, that's m times x, perhaps you want to call it that, divided by IY. So again, it's not actually too incredibly difficult. Same thing, different direction, that's all. So we're bending in the y at point A. We're doing the moment, which is still 24 kip inches. Now we need the x distance that A is from the neutral axis. So again, here's A. Our neutral axis is y this time. We need this distance. How far away is that from our neutral axis about which we are bending? And that distance, I'm going to think of it again as we take the whole width here of 6 and then we subtract off x bar. I think that would be great. You're probably looking at this going x bar was 3, so I already know what this is, but whatever. So 6 inches minus x bar divided by IY, and IY again was 81.3 inches to the 4th. And what we're going to find when we do this is 0.89 KSI. Tension or compression. Again, if we're looking at this arrow, we're leaving out of the face on the right side. So when we're leaving out of the face, again, we can kind of draw this out. That means arrow has to go up and this arrow has to go down. So again, if we're coming out of the face, then that's going to be out of the face. Again, that's going to be tension. So at A, we're in tension. Now we're going to go look at B. So at point B, again, the bending in the y direction this time about B is equal to m, same m, 24 kip inches, times x. X this time, I guess new color here. We're looking from point B here over to this y direction. So again, this is really fun. How about we take the whole distance to B again and then subtract off x bar? That's probably a really good way of thinking about it, right? So the distance to B is going to be 6 minus 1. 6 minus 1 is going to be 5 inches, minus, of course, x bar. Divided by I in the y direction, 81.3 inches to the fourth. What do we discover? 0.59 KSI. And again, it is still on the side where the arrow is coming out of the face, so therefore this is still in tension. And last but not least, we're going to do the same thing for point C. So point C, bending stress about the y direction at point C is going to be equal to M, which is still 24 kip inches for this problem. The distance this time that C is to the neutral axis, well, that is just x bar. That's lovely. Divided by I, and I again 81.3 inches to the fourth. And what we get is 0.89 KSI. And this time though, we're on the side where the arrow is going into the face, right? Arrow's going into the face over here. So this means that we're in compression. So again, kind of same thing, different directions. Again, it's the same equation. You're just looking how far away is your point from the neutral axis that you are bending about. So the distance to the neutral axis, you can call it y. You can give it a different thing if you really want to. Some people actually call it c. Some people like to say that the stress equation is m times c over I. Maybe that one makes a little bit more sense. Again, c being the distance from your point to the axis about which you are bending, and that's really all there is to it. So again, if you can't do moment of inertia and find the centroid, you're kind of screwed. But if you can do that, this is really, really, really simple, easy topic.